Okay, to see what dimension A is, what I would do is first I would see how far it is all the way out to these edges, which is the 36 inches with a 1/4 inch put onto each end. Now, just to see where you guys are at, if I have a 1/4 inch and a 1/4 inch, or 2/4 of an inch, I end up with how much? Half inch, right? So I've got 36 plus a half, that's 36 1/2 inch all the way out to these edges. So now I just take 1 7/8 inches off of each side. I can multiply it by 2, or I can add 1 7/8 inches to itself. Seven plus 7 is 14/8, which is going to reduce to 1 6/8. 6/8, of course, reduces to 3/4. Carry the 1, so 3 3/4. So from my 36 1/2, I have to subtract 3 3/4. My common denominator, I'm going to make this 36 2/4. This is going to stay 3 3/4. And I'm going to have to borrow when I subtract. So borrowing from the 6 makes it a 5. What do I have to add to my 2? 4. Good. So that's 6/4. 6/4 minus 3/4 is 3/4. And 5 minus 3 is 2 and 3. So 32 3/4 inches is the width of that top piece of my face frame. The door then, it's that dimension plus 5/8 on each side. So 5/8 times 2. Now you'll notice when it was a mixed number, I added it to itself. Just for me, it's easier to add a mixed number to itself than it is to multiply it by 2. For you, you may decide it's different. You don't have to do it that way. You could multiply it if you wanted to. A fraction, if it's just a fraction without a whole number, for me it's easier just to multiply it because in many cases this happens. The 8 and 2 cross cancel to give me 4 and 1. So I get 5/4 or 1 1/4 inches. So the width of my door is the width of that top piece plus 1 1/4 inches. So 32 3/4 plus 1 1/4. 3 and 1 make 4/4, which is just 1. So I'm going to cross that off, put 1 up there. 1 and 2 is 3, plus 1 is 4, and 3. So that door is 34 inches. Did anybody have both of those? Show of hands. How about you had the first one and just ran out of time for the second one? Just a couple of you? Okay. Does anybody have questions on that? Do we need to go over more examples of that, or just didn't have enough time? All right, let's do one more similar to that. What I'm going to look at here, kind of reverse of a problem we did last class. I'm going to have a rail on the bottom of a table that is 40 inches long. And beside that, we're going to have legs mounted that are 1 3/4 inches. Each. And then we have our top that is going to extend over 1 5/8 inches on each side. Let's redraw that just a little bit. And what we're going to do is this. We're going to put a decorative edge on this. Pretend my artwork doesn't suck. This decorative edge is 5/16 of an inch on each side. What we're going to try to do is we want to put a veneer top on this, and I want to see how wide that veneer has to be across there. So I'll give you guys a few minutes to try that. I'll give you a few more minutes than I did last time. Just to do a little process check here. I get the dimension from here to here, of course. So you're going to add 1 5/8, 1 3/4, 40, 1 3/4, and 1 5/8. How many of you have that dimension already? Or think you have something for that dimension? Good share of you? Okay. A lot of different ways you could go about this. You could go ahead and just add them all up if you wanted to. Or you could multiply the 1 5/8 by 2 and the 1 3/4 by 2, so before you add them, really doesn't make a difference. I'm going to go ahead and just add them all up. Common denominator is going to be 8, so this is going to stay 5/8. This is going to become 6/8. They'll stay 5/8. 3/4 will become 6/8. So I'm going to add my 8s first. That's my last digit. 5 and 6 is 11, plus 5 is 16, plus 6 is 22/8. So that is, where that came from, 2 and 6/8. So that's going to be 3/4. The 6/8 reduces to 3/4. We carry the 2. 2, 3, 4, 5, 6. And the 40. So 46 3/4 is from here to here. How many of you had that? Show of hands. A couple of you? Okay. From there now, I'm going to give you another minute. Now that we have the 46 3/4 all the way out to here, find what this is. I'll give you another minute to do that. So we have 5/16 on each side. So I'm going to double that first. 5/16 times 2. And this one I'm just going to cross cancel my 16 and 2 to give me 8 and 1. Then it would be 10/16, which reduces to 5/8. So now I can subtract 5/8 off of my 46 3/8. Or 46 3/4, sorry. I was jumping ahead of myself. And of course I have to change this into 8, so this will be 46 3/4 is going to be 6/8. So we end up with 46 1/8 there. Now I realize these problems are not pleasant to do. Working with the fractions is, not too many students would pick that as their favorite part of math. But, and I know it's kind of corny and I'll properly hate myself later for saying it, but if you're going to be in the construction industry, fractions have to become your friends. We've got to get used to working with them. Until the day that construction goes metric, which I'm not holding my breath that it's going to happen in my lifetime. So anyway, today we're going to move on. We're going to move on to decimals. And to understand decimals, we have to go back to our place values again and look at them more closely. So if we're looking from our decimal point working backwards, this was the ones, tens, hundreds, 1,000s, 10,000s, 100,000s, and so on. Well, if we look at those place values, as we move from left to right, if I move one spot to the right, the numerical value is divided by 10. Each time I do it, 100 divided by, or 1,000 divided by 100, it's divided by 10, or 1,000 divided by 10 gives us 100. 100 divided by 10 gives us the tens. 10 divided by 10 gives us the ones. And we've talked about this a little bit before, how our patterns in math often determine what the results are when our processes break down, or our basic definition of our processes breaks down. And here is one of those cases of a pattern that must continue. As we keep moving past the decimal point, moving over, ones divided by 10 is going to be 1/10. Moving over again, 1/10 divided by 10 is going to be 1/100th, and 1/1000th, and 1/10,000th, and so on. If those place values look suspiciously like fractions, it's because they are. Decimals are nothing more than fractions. They are specific fractions that have denominators that are powers of 10, as we see there. So if we have 0.58, what that literally means is 58 hundredths. It is a fraction, 58 over 100. Now, if we were going to convert a decimal to a fraction, that is exactly how we would do it, is we would just put it over 100. Now, we wouldn't leave it like that. We would end up wanting to, since both of those can divide by 2, we would divide it by 2 to make it 29/50ths. If I had 0.375 to turn that into a fraction, that is 375 over, the denominator is going to be the place value of the last digit. So this is tenths, hundredths, thousandths. Just a little double check here for the pattern. If there are 3 decimal places, there has to be 3 zeros in that denominator. Now, once again, 375 thousandths, we would not leave it that way because both of those can be divided. They can actually, you can probably see that they can be divided by 5, but to make it a little quicker, they can both be divided by 125. That's 3/8. Now, before we get too far into the operations and stuff with decimals, you might be wondering, well, why are we worried about decimals? In constructions, don't we use quarters, eighths, sixteenths, and so on? Well, if we get into the cabinetry side of it, I know Mastercraft here in Race Lake has gone to using decimals now instead of fractions of an inch. They produce all their stuff to within 1/100th of an inch. Now, when you're dealing with wood, getting much more precise than that isn't very possible, just because wood expands and contracts so much with climate issues, with humidity and temperature and all that stuff. But, 1/100th of an inch is still doable. So anyway, let's do some of our operations with these decimals. I'm going to assume you guys know how to round, so I'm not going to deal with that. We're going to go straight into our operations, like 8.37 plus 26.9. Now, when I go to add these, what do I have to make sure I do? Line up my decimals. Good. And as we went over back on our first class, it's not just because our 3rd grade teacher told us to. It's because whenever we add or subtract numbers, we can only combine things that have the same names. And that comes right down to the digits. So by lining up those decimal points, we're making sure that our tenths are with our tenths, our ones are with our ones, and every other digit lines up. Now, to make this workable, we should fill in that missing 0, so we have 0 hundredths to combine with our 7 hundredths. And then, of course, once we have that lined up, just like any other addition, we'll start on the right and work our way back. 7 and 0 makes 7. 3 plus 9 is 12. Now, if we were adding whole numbers, we would keep the 2 and carry the 1. What does that decimal point do to us? Trick question, right? It doesn't do absolutely nothing. We can still carry. The only thing that decimal point does is before we can add the 1, 8, and the 6, we have to bring the decimal point down. When we're doing our calculations, we cannot cross the decimal point without doing something with it. So we bring it straight down. 1 and 8 is 9, plus 6 is 15. So again, 5, carry the 1. And 1 and 2 is 3. So 35.27. Bringing that decimal point straight down, as we've noted before, is because when we add or subtract, we keep the same name. So these were tenths, they have to stay tenths. These were ones, they have to stay ones. So the decimal point moves straight down. when we go to subtract decimals, so you have 37.6 minus 9.84. Just like with addition, as you guys pointed out, we have to line up the decimal points. Now with addition, we could have got away without putting this 0 in and just brought the 7 down. For subtraction, we have to put that 0 in. Otherwise, there's nothing to subtract the 4 from. So now we go just like whole numbers, right to left. 0 minus 4 can't be done, so we borrow from the 6. That's 5, and this is now 10. 10 minus 4 is 6. Perfect. 5 minus 8 can't be done. We borrow from the 7 to make that 6, and this is now 15. 15 minus 8? 7. And now we got to remember, bring the decimal point down. 6 minus 9, again we got to borrow. So 2 and 16. 16 minus 9. 7. And we bring down the 2. So 27.76. Just like I did with any of my whole number calculations, I acknowledge that you're probably going to use a calculator on these. But I do want you to, again, do that estimation. Over here, look at this and say, hey, that's about 8. And this is, 27, 30, whatever. 8 and 27 better give me something close to 35. Same over here. This is about 38. This is about 10. 38 minus 10 better get me close to 28. One of the reasons I bring that up is on most calculators, statistically, one of the keys that tends to malfunction first, or that does not register the most, is the decimal point. Also, on many of your calculators, the decimal point does not show up until you type in the next digit. So you don't know that it didn't register until after it's too late. Now, one thing, before I move on, one thing I want to show you about subtraction is an example like this. 9 minus 2.8457. So we've said when we subtract and add, we have to line up our decimal points. Where is our decimal point in the 9? After it. Very good. That's 9 point whatever. So now we know where to line up our decimal point. 8457. And we're subtracting. And just like before, we fill in our zeros to fill in those missing decimal places. When we go to subtract, we have 0 minus 7 can't be done, so we need to borrow. But we look here and there is nothing to borrow from. So where do we go? Yeah, all the way over to the 9. We borrow from the 9, and that's an 8. So that would make this a 10. Well, we don't need it here. Well, we might need it here, but we need to get it all the way down here. So we just have to keep borrowing. Borrow from that 10, and it becomes a 9, and this is a 10. Borrowing again, that becomes a 9, and this a 10. Borrow again, that's a 9, and this is a 10. Now we can subtract. 10 minus 7 is 3. 9 minus 4, or 9 minus 5, sorry, is 4. 9 minus 4 is 5, and 9 minus 8? 1. Remember to bring down the decimal, and then 8 minus 2 is 6. Perfect. Now again, these aren't too hard to estimate. This is 9, and this is about 3. So you know 9 minus 3 is going to get you close to 6. Let's look at multiplying next. $2.47 times 6.4. So when I set this up, do I have to line up my decimal points? No, we do not. we simply put the numbers down and we start to go. Because when we multiply and when we divide, we do not need the same name. So we don't have to line up the decimal points. Just like we did with whole numbers, we'll start with the last digit of the bottom number. And we're going to multiply. 4 times 7 is 28. So we'll keep the 8 and carry the 2. 4 times 4. 16 plus 2 makes 18. So 8 carry the 1. 4 times 2 is 8. Plus 1 is 9. Now before we move over to the 6, what have we been taught that we have to do down here? Put in a 0 or leave a space, right? Now the other thing I do, I'm going to do this. I always put a line up here over my carries. That way I know that anything below the line is an old carry and I don't have to worry about it. So now we're going to go ahead. 6 times 7 is
42.
42. So 2 carry the 4. 6 times 4.
20.
24. Plus 4 is 28. So 8 carry the 2. And 6 times 2. 12 plus 2 is 14. So 4 and we carry over the 1. Now notice when we multiplied, we did completely ignore that decimal point. We just multiplied all the numbers with no concern for the decimal point at all. Now we're going to go ahead and combine, adding our columns like we did with whole numbers. 8 and 0 is 8. 8 and 2 is 10, so 0 carry the 1. 1 and 9 is 10, plus 8 is 18, so 8 carry the 1. 1 and 4 is 5, and 1. Where does that decimal point have to go? We've been taught to go 1, 2, 3 decimal places in the problem. 1, 2, 3 decimal places in our answer. So our decimal point has to go between the 5 and the 8. And that is the process you're supposed to do. And as we mentioned before, that's just combining the names. We have hundredths times tenths. That has to become thousandths. But there's another way of looking at that. This is about, what, 2 or 3? Probably closer to 2. This is 6 or 7, closer to 6. 2 times 6 is 12. I'm estimating this at about 12. 15 is a little off, but it makes sense. Would 1.5 make any sense? No. Would 158 make any sense? No. So that 15.808, that's the only place I can put my decimal in that answer for it to make any sense. And as I said, that decimal point is one of the first keys on a calculator to malfunction. So when you're doing multiplication, it is very important to estimate it and have an idea. Because if I'm punching this in the calculator, 2.47 times 6.4, I'll do it correctly here the first time. I get that answer, 15.808. But watch this, 2.47 times 6.4. My decimal point didn't register, but what do you notice is similar about those two answers? Yeah, they're the same numbers, the decimal point's just in the wrong spot. It's 15.808, but the decimal's after between the 8 and the 0 instead of between the 5 and the 8 now. So if you miss that decimal point on your calculator, you get the exact same digits, just the decimal point's in the wrong spot. So when you're multiplying, it's very important you do that estimate first to have an idea of where your answer should be. Let's look at dividing quick. If I have 9.734 divided by 3.7. Now I'm going to ask you to give me this answer to the nearest thousand. how do we divide by a decimal? Well, the answer is we don't. We've been taught you move that decimal point over. Make that 37. But what else do we have to do when we do that? Move the other one over too. Very good. So this becomes 97.34 divided by 37. Now, how is it that we're capable of doing that we're able to do that? Well, we mentioned a little bit in the last couple of classes that fractions and division kind of go together. They're kind of the same thing. We can flop back and forth between the notations. So you can make this division into a fraction like this. 9.734 over 3.7. And in a fraction, I can multiply the top and bottom by the same number. So if I want to get rid of that decimal in my 3.7, since it's only one decimal place, I can get rid of it by multiplying by 10. So if I multiply the bottom by 10, I have to multiply the top by 10. 3.7 times 10 is 37. 9.734 times 10 is 97.34. So then we go from that fraction notation back into division, and we get this. So that's all it is using that fraction notation and multiplying the numerator and denominator by the same thing. So now we're going to divide. Does 37 go into 9? No. So we'll leave it blank above the 9. Does 37 go into 97? Yeah. Goes in there twice. 2 times 37 is 74. If you don't know that, you can always do 37 times 2 off to the side. Get 74. Subtract. You get 23. Now we can. The next thing we do is bring down the 3. But before we bring down that 3, what do I have to do? Move the decimal point up. So again, we cannot cross that decimal point without doing something with it. Now we bring that 3 down. 37 into 233. Let's see, 7 I think is going to be too big. Let's try 6 and see what happens. So 37 times 6. 6 times 7 is 42, so 2 carry the 4. 6 times 3 is 18, plus 4 is 22. So yeah, that's 222. That works. We subtract, get 11. And we can bring down the 4. 37 into 114. I will try a 3. 3 times 37 is 21. Carry the 2. That's 111, right? So at 111, we subtract to get 3 left over. Now, right now, this is the hundredths digit here, and I had said I want it to the nearest thousandth. How do I keep going? How can I get to the thousandths here? We can just add zeros. Since if we're after the decimal point, we can add zeros to the end. We bring down that 0. This 37 goes into 30 0 times. So now that's the thousandths digit. Am I done? Say no. No. Well, why not? Well, because I told you to, right? We got to add one more 0 and bring it down. 37 into 300. Oh, what's that going to be? I'm going to try 8. I think it's going to go 8 times. 37 times 8. 8 times 7 is 56, so 6 carry the 5. 8 times 3 is 24, plus 5 is 29, so 296. It does work. It does go 8 times. So why did I need that digit there when I only had to go to the nearest thousandth? Well, I need to know whether that's going to stay 2.630 or round up to 2.631. This 8 is telling us it's 2.631. Now, I do realize that just like with whole numbers, long division with decimals isn't pleasant, and you're most likely going to punch it into your calculator. So yeah, you're probably looking at this and saying, hey, I got something close to 9 divided by 3. That's going to be something about 3. Or maybe you're looking at 10 divided by 4, depending on how you want to estimate it. It's going to be like 2.5. Make sure you have some sort of an estimate there. Because just like with multiplication, if you miss that decimal point when you're dividing, it'll give you the same digits just with the decimal point in the wrong spot. So now a couple of little notes about estimating with our decimals. Adding and subtracting is pretty straightforward, but I want to look at our multiplication and division estimates. So we're going to go back to estimating larger whole numbers. If I have something like 4,000 times 20, I multiplied the 4 and the 2, gives me 8. How many zeros did I need? 4 zeros. Good. I just counted the total zeros in the problem. 1, 2, 3, 4. Gave me 4 zeros in my answer. So if I have, I did have to be careful with something like 500,000 times 800. We had 5 times 8 was 40. And I have to remember that this 0 doesn't count, right? I still need to put how many more zeros on the end? 7, right? So 400 million. Well, when I'm working with decimals, I have something similar to that. If I have 0.004 divided by, or not divided by, multiplied by 0.2. Well, 4 times 2 is 8, just like it was up here. But up here, I combined my zeros. I had 3 zeros and 1 0 combined to give me 4 zeros. Down here, it's not the zeros that combine, it's the decimal places. I have 3 decimal places and 1 decimal place. My answer has to have 3 plus 1, or 4 decimal places. Notice it's not 4 zeros. It's 4 decimal places. So if I were to estimate 0.03 times 0.005. 3 times 5 is 15. How many total decimal places do I need? I need 3 more zeros, right? To make it 5 total decimal places. 1, 2, 3, 4, 5. Perfect. When I divide, when I had a division estimate like 800,000 divided by 200. I divided the numbers. 8 divided by 2 is 4. What did I do with the zeros? How many zeros am I going to end up with in my answer over here? How many? Careful. 3, there you go. Because when I divide, this has 5 zeros, this has 2 zeros, I end up subtracting. 5 minus 2 makes 3 zeros in my answer. Or I could think of it as canceling them out. I have 2 here that I'm dividing by, I'm canceling out 2 of those, leaving me with 3. So if I have 60,000 divided by 3,000, what am I going to get? 1 0, yep. So 6 divided by 3 is, you were just 1 question ahead of me. 6 divided by 3 is 2, and we do have 1 0. We cancel off 1, 2, 3, 1, 2, 3, we're left with 1 0. Perfect. when we work with decimals, it's a similar pattern, just like it was with multiplication. If I have 0.0008 divided by 0.04. Remember, with decimals, it's not the number of zeros, it's the number of decimal places. So I have 8 divided by 4 is 2. Here we had 1, 2, 3, 4 decimal places. Here we had 2. So how many decimal places am I going to have in my answer? 2. 4 minus 2 is 2, so I have 2 decimal places there. So if I have 0.00006 divided by 0.03, of course 6 divided by 3 is 2. How many decimal places do I have? 3. Very good. This has 1, 2, 3, 4, 5. This has 2. 5 minus 2 is 3 decimal places. Or you could just cancel out. 1, 2, 1, 2. I'm going to have 3 decimal places. So estimating with our decimals is not as hard as one might think. It's the same, very similar processes as estimating with our whole numbers. Okay, so now we've already looked at converting decimals to fractions. We had, 0.0625, and we could convert that into a fraction. In your notes, quick, I want you to see if you can remember how to turn that into an exact fraction. So 0.0625. Oops. There you go. Sorry about that. So this is going to become 625 over what? 10,000. Good. And then they can both be reduced by what? What's that?
16.
They'll reduce to 16. Both of them can be reduced by 125. Or 5 or 25. This is going to become 5 over 80. This can still be reduced by 5. Give me 1 over 16. Anybody get 1/16? Perfect. Okay. What if we have 7.84? And I need to convert that to a fraction. Well, the part in front of the decimal point is a whole number. Just like we have mixed numbers with our fractions, we have mixed numbers with our decimals. That 7 is not going to change. It's the 0.84 that we have to convert to a fraction. So that's going to become 84 over 100. Great. 2 decimal places, so 2 zeros in our denominator. Both can be divided by 2, giving us 42 over 50. Are we done? Nope, they can both be divided by 2 again. Give me 21 over 25. That's as far as we can reduce it. We have to make sure we put it back with the whole number, 7 and 21/25. So now that's great to be able to convert a decimal into a fraction. But in construction, that's not always necessarily useful. We don't have a 21/25 drill bit in our tool set usually. So a lot of times in construction, we need to be able to convert that to the nearest 16th or 32nd or whatever of an inch. So to do that, let's say I have 0.713 inches, and I want to convert that to the nearest 16th inch. What I'm going to do is I'm going to take that decimal, 0.713, and rather than putting it over a denominator that's indicated by its decimal place value, I'm just going to put it over 1 and make it a fraction like that. Notice the decimal point is still in there. It's still 0.713, it's just over 1. But it is now technically a fraction. It's not a pretty one, and we don't like having that decimal within our fraction, but we're okay with it. We can deal with it. Right now, our denominator is 1. What do we want the denominator to be? 16ths. Perfect. How do I change a 1 into a 16 in a fraction? I'm going to multiply by 16. So 1 times 16 is 16. But if I multiply the bottom of the fraction by 16, I have to do the same to the top. Good. So 0.713 times 16 is 11.456. Did I? 7.13, shouldn't it? 0.713. Thank you. Nice catch. 11.408. Thank you. Okay, so now what is this telling us here? Well, this is telling us that this is between 11/16 and 12/16. Which one is it closer to? 11. It's 11.4, so it would round down to 11. So let's say we have 0.219 inches, and I want that rounded to the nearest 32nd of an inch. So again, take my 0.219 over 1. What am I going to want to do next? Times 32 on top and bottom. So 1 times 32 is 32. 0.219 times 32 is 7.008. So again, this one's telling us it's between 7 30-seconds and 8 30-seconds. This one's pretty easily closest to 7. Good. I want you guys to try one of your notes. .398 inches to the nearest 16th of an inch. See what you come up with for that. So we make it 0.398 over 1, and then times 16 on top and bottom, And we get, what, 6 point something?
6.30.
0.30? 0.368, right? So we're between 6/16 and 7/16. Which are we closest to? 6. Now, this is why I always get questions on this. I'm going to reduce that to 3/8 because both of those can be divided by 2. Well, the question I always get is, well, didn't you say you want it to the nearest 16th? Why'd you reduce it to 3/8? Well, 3/8 is a 16th. I mean, there is no, if you look in your toolkit, your drill bit set, there is no 6/16 in there. There's a 3/8. So even once you've rounded it to the nearest 16th, you can still reduce it because that's the tool size you're going to be looking for. That's the spot on your tape measure you'd be looking for if you're measuring something out. So what if we have 7.8449 inches, and I want to go to the nearest 64th of an inch. What am I going to do with this 7? The answer is nothing. I'm going to take the 7 off and only work with the decimal. So 0.849 over 1. And then? Perfect. Times 64 on top and bottom. So 0.849 times 64, 54.336. And of course, that is going to be between 54/64 and 55/64. Closest to which one?
54.
54. Am I going to leave it as 54? No, we're going to divide it by 2. 54 divided by 2 is 27. 64 divided by 2 is 30 seconds. So that is 7 and 27 30-seconds of an inch. I'm going to have you guys try one with a whole number on it. We're going to have 8.974 to the nearest 16th inch. See what you come up with. Okay, so we have to take the 8 off of here. And we're going to work with the 0.974 over 1. Then we're going to multiply by 16 on top and bottom. So 16 on bottom, 0.974.
15.584.
Okay, good. 15.584. Thank you. 0.584. Okay. Now that is telling us this is between 15/16 and 16/16. It's closest to 16, right? That's a 5, so we're on 16, which means somebody said it. That's just 1. So this gets rounded up to 9 complete inches. To the nearest 16th, that's closest to 9 inches. How many of you had that one? Good deal. I want you to try one more. 3.052 to the nearest 1/8 inch. See what you come up with there. Okay, so we keep the 3 inches, take the 0.052 over 1, and then times 8 over 8 gives us 8 on bottom, gives us what? 416, which of course rounds to 0, so that's just 3 inches. Good. Okay, that's it for new material, but there are a couple of comments I want to make on the quizzes. A problem that was missed a lot, and it's one that there was a couple of examples in the homework, but I didn't go over anything in class, so I didn't take points off for it. It was on the first quiz. It's looking if we have like a stud wall. And let's say we have a stud wall that is 272 inches long. And the studs are spaced 16 inches on center. OC stands for on center. So we need to ask, how many studs are we going to put in that wall? And most of you correctly started out 272 divided by 16, which is 17. Good. But there's a problem with that answer. To figure out what the problem is, let's take a look at a smaller example. Let's say I have a 48-inch wall. Now I'm going to put my studs still 16 inches on center. If I do 48 divided by 16, I get 3. So if I'm looking at this, I've got a stud here at 16 inches. I've got a stud at 32 inches. And I've got a stud at 48 inches. What's missing there? The one at the beginning here, right? The one at the first stud. So when I take that length and I divide by the spacing, I leave out the stud that's at 0 inches. So I have to add 1 to it. I need 4 studs to cover that. So up here, that's 17, I would have to add 1. I need an 18th stud so that I have one at 0 inches. Dividing out doesn't account for that. Similar thing happens. You have a foundation and you're putting floor joists or floor trusses on it. Let's say that this here is 48 feet long. And we're going to install floor trusses at 2 feet on center. How many of those floor trusses is it going to take? Well, tell me what to do. Heard somebody mumbling there. 48 divided by 2, which gives me 24. Is that my answer? No, what do I have to do? Add 1. It's going to take 25. So 25 floor joists or floor trusses. That's assuming there's one at the beginning and one at the end. Now there are cases where I don't want joists at the end. in Minnesota and in some other areas, building code does not allow for a floor truss or floor joist at the end of the building. What they require you to do, it's a term you probably haven't heard yet, is something called balloon frame. So on the end of the building, looking at this from the end, on top here where the floor joist would sit, the rest of the building, above the wall, they actually require you to build like a little stud wall, and then put your, so you can put insulation in there to insulate the ends of that, just like you would any other wall of the house. It's an energy efficiency deal. But there are places where building code requires that. So you would not put joists on the end of that. So let's say we have a house here that is 38 feet long. And we're again installing floor truss or joists at 2 feet on center. How many are we going to need? Well, what's our process? 38 divided by 2 is 19. Why'd you say 18? Perfect. Need to subtract 1. When you do this division, it gives you all the ones that you're going to need in the middle, plus 1 at the end. So when you do that, either you're going to have to add 1 to put 1 at the beginning, or you have to subtract 1 to get rid of the 1 at the end, depending on whether you have them at the ends or not. There was another problem. So I mean, that was one of your problems on that quiz 1, of finding how many joists it was going to take if you had so many inches and they were spaced. I don't remember if it was 16 inches apart or what the spacing was now. Then there was another one similar to this. Let's say that this is 36 feet. I don't remember the dimensions off the quiz. I'm pretty sure it was 48 on the quiz, but let's say that's 36 feet there, and this is 64 feet. And we are going to space beams or girders across here 9 feet apart. We want to know how many feet of beam, how many linear feet of beam we need to complete that building. Well, first of all, we need to know how many beams, number of beams. To figure that out, we've got 36 feet divided by the spacing, which is 9 feet, which gives us 4. What do we have to do to that 4, though? We're going to have to, do we need them at the edges? No, we don't need them at the walls. So we have to subtract 1. You get 3. There's going to be 3 beams. So then to get the length or the linear feet, each beam is 64 feet times 3. For this example, that'd be 192 feet of beams. Your numbers on your quiz are slightly different. Any questions? Okay. Some pages of homework. In the little book, we have units 11, 12, 13, and 14. The odds. Again, remember, check them over in the back of the book to get your answers correct. If some of them are really easy, feel free to skip ahead to the more difficult ones in that section. Anybody have any questions? Okay.